So in chapter 10, we are gonna have heat transfer, right? So heat transfer is very useful for combustion. It's very useful for air heat exchanger. There is a lot of applications where you actually need to put heat, or actually heat just happen because the duct is not really insulated. Heat transfer would happen. So to solve our problem easily, we will just ignore the friction for now. And then we will put the friction and the heat transfer together. Alright? So this is duct without friction, only heat transfer. And the heat transfer can be in or out of the duct, plus or minus. When we add, it's plus. When we take it out, it's minus. Right? Just like the first law of thermodynamics. You add Q, it's plus. You take it out, it's minus. And in chapter 9, when we had no heat transfer but only friction, we call it fan of flow. This time we will call it Rayleigh flow. And in fan of flow we use appendix F. Over here we're going to use appendix. And look at it, has Rayleigh, it has G in it. Isn't that nice? Right. So what is the deal? The deal is you have the inlet condition, and you know how much delta Q. This is how much heat per kilogram of the stuff going in. Alright? Delta Q is the kilojoule per kilogram. So if you know the m dot, you can figure out how much kilowatt is coming in. And we would like to find the stuff at the exit. New Mach number, new pressure, new temperature, new everything. So, what do we have in our hand to solve for the flow out on the outlets? We have continuity, momentum, and energy equation. We'll write them, we'll solve them, the book will solve them. And we will have equation to use, or the appendix which will have those equation in. Right? So the continuity equation, just like fan of flow, rho v equal constant. It was m dot equal constant, but the area is constant. That's why it become rho v. So the velocity and the rho, basically one of them go higher, the other one has to drop, so that you maintain the rho v equal constant. Right? That's the first equation. Second equation is the momentum. And notice how there is no friction in this fan, in this Rayleigh flow, no friction. But still there is a pressure change. No friction, but there is a pressure change. Why? Because we are heating, temperature is changing, the velocities need to maintain its balance with the density, so that will change the pressure. So here is the pressure at the inlet, here is the pressure at the outlet. When I say P plus delta P, I don't mean it will increase. I'm just saying P plus delta P. Delta P can be plus or minus. And V, and here is dV. V plus dV. And so here's the control volume that we have, and the momentum equation will be the pressure force, and there is no shear, so that's why the only thing that we have is the pressure force, equal to unsteady term that's not here because it's steady, plus equal to m dot, that's rho v, that's m dot, v out minus vn. V out is v plus delta v, and vn is v. This becomes the momentum equation. Right? Continuity, momentum equation. And the energy equation is the first law of thermodynamics. And in the fan duct, the Q was 0 because it was adiabatic, and the work was 0, and that's why we said H total is constant in the fan flow. That's why we said it's T naught throughout the duct. This fan duct, all this curve has the same T naught, different T but the same T naught, because energy was not allowed to come out. This time there is Q. And therefore, of course, T naught will be different. Okay? See how in the fan of flow the friction was there, the FL over D was the reason why the Mach number was changing. Remember the equation that we used? FL max over D equal FL max over D plus FLD. The FLD was really the reason why the thing were happening. The Mach number was changing. This time it's the Q. Alright? That's changing things. And actually, this equation, the Q is m dot H total minus H total. H total is what? It's kinetic energy plus enthalpy. Or basically, you can just say that this is Cp T total. Q is CB T naught 2 minus T naught 1. This equation is the equation that you have to write in every single problem. Okay? Just like in the expansion fan, we always start with turning equal nu2 minus nu1, and that's how we solve the problem. And in the Fano-duct, we say FL max equal FL max plus FLD. In any really flow problem, you have to write this equation. That's the reason why things are happening, because the Q. And it's simply the energy equation, huh? But it's written as in total enthalpy. So CB T naught 2 minus T naught 1. Okay? And if you just multiply the whole thing by m dot, this become Q, capital Q, and this become m dot H total minus H total. That's the energy equation. It's nothing new. Those three equations, you solve them together. The book did solve them together, and we end up getting 10.8 and 10.9 and 10.11 and 10.12 and 10.13 and 10.15, and those are what? P2 over P1, T2 over T1, P over P star, T over T star, and V over V star, and B naught over B naught star. What are the star? That is the Mach equal 1 at the end. That's the, so they're just like in Fano flow, this ready flow duct also are approaching Mach 1. If he's supersonic, he will slow down. If he's subsonic, he will speed up to hit star at the end. And if we give him enough Q, we can choke him. We can make him go to star condition. All right? And so I just want to jump first to show you the chart. There's actually, sorry, a curve. It looked very similar to the Fano duct, right? Except that, so this is again TS diagram. Okay. This is the TS diagram, and this is top. The top is subsonic, and the bottom is supersonic. And that point at the end, just like the Fano flow, that is the sonic point. And there is a very, the point here on the top, you know, the highest temperature ever, that's basically for what Mach number? Square root of 1 over gamma. And adding heat transfer to a duct without friction should increase or decrease the entropy. Adding heat transfer, adding Q should increase the entropy, right? So this is heating. If I add Q, I will go this way. And if I cool down, there is no friction, meaning the only reason why the entropy will change is because of the heat transfer, right? Then we can change for two reasons, irreversibility and heat transfer. So heating will take me this way, heating will take me that way, and cooling will take me this way. It will decrease the entropy. So if I heat the subsonic flow, I'll go this way, this way. That makes sense. The temperature is getting higher and higher because I'm heating. That okay. Oops, what happened here? You add Q and the temperature will drop down because the entropy needs to increase, right? And if you are adding heating in the supersonic flow, you will go like this, like this, like this. But once you reach that point, adding more Q in the flow, like in a scramjet engine, cannot take you this way. Adding more Q than what it will take you to hit Mach 1 at the end of the combustor will actually make you move to another curve. It will choke the flow. All right. So that's when in the homework problem, he will ask about what is the maximum flow rate and that we can add in that combustor. It's obviously the amount of Q that will make us go to Mach 1 at the exit, the star condition at the exit, right? And the same thing for subsonic flow too. There is a maximum Q, again, that will get you to star condition at the end. All right? So you are welcome to use all those equations, okay? Or use the appendix G. So appendix G basically have the Mach number and had all those equations on them. T naught over T, everything is basically in terms of T star. T naught over T star, T over T star, P over P star, V over V star. If you know the Mach number at 1, you can get T1 over T star, and then if you know the Mach number at 2, you can also get T2 over T star, and that's how you'll be able to solve for T2. So that cartoon that I'm always making, here's 1 and here's 2. So if we know Mach 1 and if we know Mach 2, and I know T1 and I'm asking about T2, where this is a star condition. Meaning from M1 appendix G, I can get T1 over T star. And this allow me to get T star. And then knowing M2, again appendix G, I can get T2 over T star. And now since I know T star, I can get my T2. And the same thing for the pressure, right? The big question for a free homework problem.
How do you solve M2?
How do you solve for M2? How did we get this M2?
That was the big question, right?
That is a big question, right? So how do you, because I need M2 so that I can solve for the pressure at 2 and the temperature at 2. And so can anyone tell me how you can get the Mach number at 2? No. For a free homework problem.
I want to say it has something to do with the equation Cp delta T.
Yes. Tim. Huh? No, I cannot use the final flow. There is no friction in this. This is Rayleigh flow. You're just adding heat transfer.
What do we know and not know?
We know the Mach 1. We know that, so given is M1, T1, and Q, the small q, and required is T2. So I explained to you that if I know M2, I will just do this. From M1 I get T1 over T star, and from M2 I get T2 over T star. And that's how I can get T2. This depends on the fact that I know M2. So how can I get M2?
Q equals CP delta T.
Q equal, C, the small q is CB T naught 2 minus T naught 1. So how is that helping, John?
Learn the other temperature, T2.
So you are saying let's get T naught 1. That's probably why Etienne is saying let's go to appendix P. Is that the reason why? Not really, huh?
No,
but the only way to get T naught 1 is I know M1 and T1. How can I get T naught 1? Appendix B, right? Appendix B will get T naught 1. But let's go with John. So John, I have T naught 1, right? And I have Q, and you are trying to give me M2 for a free homework problem.
And we know CP from.
Yes, we know CB because this is air, or it will be given for us.
So that gives us T naught 2.
Yes. I need my M2. You're there. You're almost there. You're almost there. Give me my M2. Get your free homework problem. Anyone else for a free homework problem?
Well, since you would have the M1, you can use M1 to get the T star or the T naught star, and then with the T naught star and T naught 2, you can get M2.
And Kenny had a free homework problem. Sorry, John.
So what table do you go to for that?
So John is right in using this equation. I told you, you cannot solve any problem without this equation. This equation is the reason why things are happening. So he used T naught 1 and Q to calculate T naught 2. Now how am I going to get T naught 2 to give me M2? So think about this appendix here in front of you and tell yourself, to find M2, I need to know one of those guys. One of those guys can give me M2. Which one do I know? I just calculated T naught 2. So Kenny saw that only if I know T naught star. Only if I know T naught star, I will have T naught 2 over T naught star. So how did he get T naught star? He said, let's use M1. So from M1 and this appendix G, you can get T naught 1 over T naught star. and from that T naught star, we basically get T naught star, and then T naught 2 over T naught star. This is how you calculate your M2. And it's following exactly that concept again. From M1 and T naught 1, we calculated T naught star. And once we know T naught star, and we know T naught 2 from this equation, we will be able to calculate M2.
So how do we calculate T? Like I'm trying to.
How to calculate T naught 2?
Yeah, T naught 2.
That's the most
Okay.
important part, right? And that is basically this equation, that the Q, the joule per kilogram that we are adding to this combustor is CB T naught 2 minus T naught 1.
Oh, I thought that was just T1, T2.
No, because this is the energy equation and it's the total enthalpy that's changing because of the Q. Not just the static enthalpy, it's the total enthalpy. If you don't get this equation, you will screw up this problem. You have to understand this equation. This is the joule per kilogram that you are adding, so this is plus, and if you are subtracting, it's going to be minus. And that's how the T naught 2 change with respect to T naught 1. The energy content of that flow is adding or increasing or decreasing depending on the Q.
Where did we get CP?
CB is given. That's the property of the fluid.
We only had M1, 2, and
I'm
Q,
sorry.
so that's why I was kind of confused at where
So in the exam, you will find out that basically he always say, he doesn't say,
or not.
or not. But in the final you find out that he says CB of air is 10, take CB of air 1004 unless otherwise mentioned. Because you need that CB for solving the, obviously, this equation. It's also in Appendix H, correct. Alright guys? So here are the procedure for solving those problems, really flow problem. Always use this equation. You know the stuff T naught 1 and the Q, you'll be able to calculate T naught 2. Once you have T naught 2, you can use it this way. That's what Kenny had the free homework for. Using M1, you can get T naught 1 over T naught star. That will allow you to get T naught star. Once you have T naught star and T naught 2, this will allow you to get M2. If you have M1 and M2, you can get anything. If you have P1, you can get P2. If you have T1, you can get T2. If you have P naught 1, you can get P naught 2. Okay? Questions? I actually think really flow problem is as easy as expansion fan problems. They are not really that complicated. Surprisingly, some students basically don't even touch the problem. They just they sell this chapter. They're like, we don't even go there. Although, when you think about it, it's not really that hard. I mean, if you understand this thing and you know that this equation is the key, then the real flow problem is not really hard at all. Right? Question about this? Very good. So here's the typical problem. Right? M1 is given, CB is given. Right? And here I'm saying watch out for the unit. One student last midterm lost the final answer just because of the R. The R, it's supposed to be it's not supposed to be 0.287. It's supposed to be 287. And there was like B over RT. So you keep this in kilopascal, and you keep this guy in kilojoule, then it's okay. They cancel. But then come the square root of gamma RT, and doesn't cancel if you screw up the R. So 20% off. So my advice is don't write kilopascal. Tell yourself there is no kilo in this course. Just say multiply by 10 to the power 3. And this 10 to the power 3. So this way you always, and I mean, I'm not saying let's use the calculator. I mean, you can cancel the 10 to the power 3 with the 10 to the power 3. But just make sure that there is always, everything is in joule. Not kilojoule. So all the stuff at the inlet is given, including gamma and R and CP, right? And here is the Q, 50 kilojoule per kilogram of air coming in. And you would like to calculate the stuff at the outlet. M2, P2, and T2. And so if this Q is being added by, say, for example, injecting fuel, and next class we will calculate what happened to the gamma and the R because of that combustion? What do you think? Will the R, if I start with air and I dump fuel, will I get different R and gamma or the same R and gamma? Why it's going to be different? Not the temperature, really. It's
Density change.
the CO2 and H2O that will come out. When you burn the fuel, you start with air, but you finish with CO2 and H2O. When I was coming today, I was looking at the sky, and there was this one airplane, and it was this huge, exhaust, and it was like marking the sky of Tulsa, basically. It means it was like a cloud, basically, behind the airplane. That's all H2O condensing. Well, today was perfect temperature, I guess, for condensation. So we completely have different composition over here. However, having said that, in this chapter, he assumed, for simplicity, same CP and same gamma and frozen composition. Nothing changed. He adding this fuel or burning, and still you end up having the same gamma and CP. Even, how about the M dot? Will the M dot leaving here would be the same as the M dot over there? Higher, lower? Higher, because of the fuel you're adding, right? But this equation over here, it's basically saying M dot CB T02 minus M dot CB T01. It's assuming the same M dot. So again, that's a simplification. The real truth is that no, M dot 2 is probably higher than M dot 1. However, why could they do this, or just how could they sleep at night with this,
Just
with what they did?
short distance, so
It's because the air to fuel ratio in all those engines are usually very big. The air to fuel ratio, meaning that you put a little bit of fuel for a very large amount of air. So the mass of the fuel is not really that big compared to the mass of the air. So you can get it's still the energy, this Q, it's of course, it's coming from burning the fuel, right? And you can calculate this as M dot fuel. This equation is important, by the way. So let me clean up and write it so that because you are going to use this for one of the homework problems. Okay, so what I'm saying is M dot fuel multiplied by the heating value of the fuel, that's a new term. So this kilogram per second of the fuel you are burning, and in one problem he's asking how much fuel we need to burn, multiplied by the heating value of the fuel, that's the kilojoule per kilogram. For every kilogram of fuel I'm burning, how much joule I'm going to get out. And that we will do next week. This is the Q dot that we are getting in our combustor. And this is the M dot air, CB T02 minus T01. If I divide everything by M dot, and over here also 1 over M dot air, this becomes the small q. And this becomes the equation that we know, that the Q is CB T02 minus T01. Right?
Is that heating value the high heating value or the low heating value?
That's an excellent question, and those people don't know the difference. Let's not talk about it. So what Ethan is saying that the heating value are two the value of heating value. One of them is overestimated, the other one is underestimated. One of them basically assuming all the water leaving the exhaust is actually steam, which is the case. And the other one is assuming that all the water leave just drop as water droplet coming from the exhaust. That gives us even more Q, because the water is not taking anything out with it. It's just water. But if it's leaving at steam, it's spoiling its latent heat from us. So that leaves very little for the engine, or a little bit less for the engine, right?
Is that why some aircraft take off with, they add water, they take off?
No, this is just the calculation of what is the heating value. So surprisingly, actually, the power plant in Europe, they use something for the calculation, for estimating how much heat. They are using the more accurate one. They use the lower heating value, but in the US, for cool or something, they use the higher heating value. Although you don't have the higher heating value. You will never get it because you don't let the water leave as water droplet. You always send it as a steam. But then I guess they take care of it later on in the calculation. But that's the difference between the two of them. Let's leave this for next class. But my point is, you see, m dot, that's what you need in the homework. M dot fuel over m dot air multiplied by the heating value, whether it's higher or lower, right, will be given to you. Cb T naught 2 minus T naught 1. This is, again, this is equal to the Q, right? That's what you need to solve the homework problem. Is this equation is correct?
Looks correct.
No, it has a mistake for a free homework problem. Huh?
Haven't got on the right.
Yeah, but you already had a free homework problem. You cannot get another one. So John is saying, right, it's the m dot. See, you are still saying m dot air CBT naught 2 minus m dot air CBT naught 1. It should have been m dot air CBT naught 1, but when it comes to the exit, it should have been m dot air plus m dot fuel CBT naught 2. That's what leave, right? But we are just assuming m dot air because it just makes the solution easier. Are we justified to do this? Yes, because again, m dot air plus m dot fuel, this number is smaller compared to this one. 1 over 10, so 10% error. So that's okay, 10%. Right? Of course, the bigger error we are making too is in, what else is wrong in this? We said that today for a free homework problem. What else is wrong? Huh?
The heating values, the high heating value versus low.
No, that's, I didn't write which one. I just said heating value, so I didn't make the mistake yet. Who said the CP? Eddie?
We both did.
All of us.
All of you? Really? You said it all at the same,
They pretty much did.
not even a fraction of a second? You said it earlier? Right. The big mistake, of course, is that CP. How do you make the CP of the air is the same as the CP of the exhaust? Even if the exhaust has the same mass flow rate, okay, we buy it, 10% error, but the CP of the CO2 and H2O is the same as the CP of the air, O2 and N2? No, it's not. But you basically, if you want to solve it with a pencil and a piece of paper, you have to do this. But if you have a computer code, of course, no, you, here, this is the equation and let's iterate to get it right. We make the CB function of the composition and we make the CB function of the temperature too. CB is never really a constant. CB is function of temperature. But this again require a lot of iteration to get it. But in that homework problem, you will just use one CP and you will even neglect the m dot fuel at the exhaust. You'll just say he go with m dot air and he leave with m dot air. It doesn't mean that you neglect m dot fuel in this part. I mean, if you say, I don't have that much m dot fuel, no, just make the Q 0, and there's no problem. You neglect it here when it comes to m dot 2, but you don't neglect it here when it comes to the Q. Okay, does this make sense? All right, so again, what's this about? He got the stuff at the inlet, he know the Q, and he's wondering what happened at the exit. So use this equation, calculate T naught 2, knowing T naught 1 and the CP, you calculate T naught 2, and then knowing M1, you can get T naught 1 over T naught star, that will allow you to get T naught star, and T naught 2 over T naught star will give you M2. That's the Kenny approach, basically, for solving this problem. All right, and once you have your M2, then you can get all the star stuff, T over T star, P over P star, and all those things allow you to get P star and T star, and that's how you can basically jump between 1 and 2 to get T2 and P2 and P naught 2 and questions? Very good. And we look at this curve, and we said heating will take you this way, cooling will take you that way. Heating and cooling. All right? So this is heating the supersonic flow. This is heating the subsonic flow. This is cooling both of them. Right? And that's really weird because cooling will take the temperature up while heating will take the temperature down. But that's what the second law is saying. But actually, it's very hard to go there practically because it takes a lot of Q to actually, when the curve flatten up like this, it takes a lot of Q to actually make the temperature change. So what happens if you choke the duct, you add even more Q, it will move you to another curve. It will lower your m dot. Alright? Let's solve this problem. How much Q? This time is asking for how much Q will it take to do what? To choke the duct. Right? So what's given? M1, P01, T01, basically the stuff at the inlet, the dimension, D5 centimeter, and to choke the duct, that means M2 should be 1, right? So he's 1 point, that's like a typical scramjet engine. Say M1 is 1.8, and you're just wondering how much fuel I could burn. You want to burn as much as you can so that you generate even more energy, so that you generate huge V exit at the back, so that you propel yourself, right? But there's a certain amount of heat. If you add even more than this, you are slowing down your duct. You are slowing the mass flow rate. So he's asking about this Q. So how can I get it? I'm going to leave this equation because we will always need it. So again, M1, and let's say B1 and T1 is given, because you know that from B01 and M1 you can get P1, and from T01 and M1 you can get T1, right? So T01 will give us T1 and P01 will give us P1. If you don't remember, let me know after the class. And we need 2 to actually be the start condition. And so the question is, how much is this Q dot to do that? Required Q dot max. And by the way, this Q dot max in kilowatt, he's asking for. Some students lose point because they just calculate the small q for me. Well, the small q units are, what's the units of this guy?
Joule per kilo.
Joule per kilogram of air going through. This is important. It's not per kilogram fuel. That would be the heating value. It's per kilogram air going through. So that Q is not what he's asking for. This Q dot in kilowatt, how can I get it from that small q?
M dot.
M dot air. Very good. M dot air multiplied by the small q. So really what's required then is Q max then, the small q max, so that we multiply by M dot air so that we can tell him. Can anyone give me this guy? Knowing the stuff at the inlet and knowing that the exit is the start condition.
You'd have to do your pi over 4 delta, because wasn't D given?
Of course, we will do the M dot air, but that's a minor thing. What I need you to focus on, what is the key, where is the beef? What is the equation that will actually give me the Q?
Oh, well, that's the Q equals CP delta T.
Right, this one. So from this one, how should I say it? Q max should be equal to CB
T naught 2.
T naught star minus T naught 1, right? That's what will make it max. If T naught 2 is T naught star, right? I know T naught 1. How can I get T naught star? M1. Excellent. M1 appendix G will give you T naught 1 over T naught star. And you are done. You got your T naught star. Right? So Q is CB T naught star minus T naught 1. Alright? And this will allow us to get T naught star from M1. That ratio is 0.8. Therefore, T naught star is this much. So now, the only thing is waiting between the capital Q and the small q is M dot. So that's why he's doing the M dot, and that's why Robert said, let's calculate the area, because you don't have the area, you only have the diameter. So he was trying to calculate the area from pi over 4d square. Okay? Questions? All right. You're done with this problem. No, I still have 11 minutes of your life. I want to use them. All right. See, this is very similar to the homework problem, I think. See, required m dot fuel over m dot air. So he's asking about the Q in an indirect way, basically. He said m dot fuel over m dot air to make T2 at the exit 1000. You want to heat the fuel, or sorry, heat the air all the way to 1000. Huh? Maybe it's not T naught, maybe it's not T2 star, but it's close. And then he's asking also for the max. So this time, what's required, what's given is not that T naught 2 is T naught star. It's actually T2 is given to us. Right? So this is what's given, T2. And required is really Q dot. Huh? Because then it's the m dot fuel heating value over the m dot here. No. That's the small q. So when he asks for m dot fuel over m dot air, he's really asking for the q. Right? And if you ask for m dot fuel over m dot air, he's asking for the q. And the heating value is given there. It's given there. And by the way, this is a nice number to remember. If you go for your job interview with Halberton or ConocoPhillips and they ask you, what's the heating value of our crude oil? Remember, they are of order of 40,000 kilojoule per kilogram, or basically 40 megajoule per kilogram. So, guys, how can I get my Q? Our equation, QCB T naught 2 minus T naught 1. And so we got our T naught 1, or we will get it because, I mean, we have T1 and M1, right? Right?
Right.
I don't see M1. Where is M1? It's kind of given because we have V1. We have V1 and T1. Of course, we can get M1 from V1 and T1. And also from having M1 and T1, we can get T naught 1. So obviously what's standing between me and the Q is the T naught 2. Can anyone help me get T naught 2?
Well, you have your T2, so you can do your T.
I don't know M2. If you are saying let's use M2,
I said T2.
how do you get me? How are you going to get T naught 2? We only have T2, and I need T naught 2 so I can calculate the Q. That's what is after. So what is your plan to get T naught 2 from T2?
Using T star from M1.
That's a great idea. So from M1 we can get T1 over T star, and this allows to calculate T star, right? And then
You use the same T star and we'll go back.
T star over T2 will allow you to get,
Will allow you to get your M2.
allow you to get M2 and all the other
Everything else
stuff
like
at
that,
2. Right, so let's write it here. So basically what I'm saying is at M1 you can get your T1 over T star, and since you know T1 you can get your T star. Now at 2 you can get T star, T2 over T star, and this allows you to get M2 from appendix G. Of course, everything is appendix G. M2 and T naught 2 over T naught star. That's what we're really after. And at 1, you need to do the same thing. At 1, you need to get T naught 1 over T naught star, because this will allow you to get the T naught star. All right? So this is your T naught 2. And back to the equation. Now you have T naught 1 and T naught 2, you can get your Q. And the second part, when you said, well, what is the max? Obviously the max when T naught 2 is T naught star. I don't really have to go for M2. I will just from 1 From M1, I will just go and get T naught star. That's the T naught 2. Good. And that's the solution over here, okay? So here is his equation. He basically figured he needs to get T naught 2 and T naught 1. From M1, he's going T naught 1, and this is what Robert said. Let's, from M1, get T1 over T star, and this allows to get T star, and then T2 over T star. Now is given, and this will allow us to get M2. And once you have M2, you can get T naught 2. Right? And you are done with the Q. And that's the second part when you assume T naught 2 is T naught star. Okay? Questions? Alright, so now this is very important. I still have 6 minutes. This is actually very cool. And this comes in also in multiple choice in the final. What are you looking at is a shock wave in a duct. And he's basically saying that if we plot the Fano curve and the Rayleigh curve that intersect at that point, the second intersection is the M2. So the normal shock solution is basically jumping between, if you look at the normal shock table, it would be this M1 and that M2. This P1 and this P2. How come? Because you remember how did we plot the Fano curve? Two equations. We used two equations to plot the Fano curve. What are those two equations? Continuity, rho v equal constant, and
Momentum.
no, the momentum gave us the FL max over D equation.
That's right.
It was the energy equation. It was that the duct was adiabatic. So just using Fano flow, continuity, and energy equation, we plotted this curve. The continuity is conserved in the shock wave. Yes, rho v is constant. And the shock wave is adiabatic. There is no energy transfer. Why there is no energy transfer? Because it's so thin, there is no chance to. So the shock wave apply or basically follow the Fano curve. If one point is here, the second point also need to be on that curve. And for the Rayleigh flow, that curve in Rayleigh curve, this came from also continuity, rho v, and no, actually momentum. So the energy equation in Rayleigh flow, that's how you get this. How you get the Q, but it's the momentum equation of the Rayleigh flow that what give you this curve. What is the equation? There was no friction at the wall. That was the momentum equation for the Rayleigh. So there is no friction on the wall of this shock wave because it's so thin again. So that's why those two guys work. Okay. Now in this page, this is one problem in your homework. So I have to give you in the next 4 minutes. There's one whole problem that basically asks you to solve isothermal flow. This is the easiest ever, really. I mean, this is even easier than expansion fan. What is an isothermal flow? It's a pipe that is not insulated, but also it's a pipe where the material, the conductivity is so high and the heat transfer rate is so quick. Air is blowing into it or something and the wall is so thin, or the flow is moving inside so slow to the extent that the heat transfer is always catching up with any change in the temperature of the flow. The moment that he would like to get a little bit heated, it's immediately cooled. Think about basically maybe oil line under the sea, under the Gulf, where there's the heat transfer of the water is so big. The heat transfer by convection wouldn't allow the gas, natural gas inside, to even get a little bit hotter or colder. Why? Because the water immediately take any extra energy or any extra increase. So if T is constant, by the way, isothermal flow doesn't mean it's frictionless. There is still friction. The only thing it means, and that's what you need to use in the solution, is the fact that the temperature is constant. So if the temperature is constant, you have all those nice relations. You will actually solve one of the homework problem by the fact that P over P is M over M. How come? How come P over P is M over M? So because the temperature ratio doesn't change, then that make M over M is V over V. Alright? Of course, because the Mach number was V over A. And because the Mach number, because the V over V, the V over V is the same over like rho over rho Y. Or actually the opposite. Why the V and rho are related like this? Inverse. Why? Why they are inverse, right? Why rho 1 over rho 2 is V2 over V1? No. Flow rate is the same. Rho V is constant. Okay, that's why rho over rho is V over V. Rho 1 over rho 2 is V2 over V1 because rho V is constant in a duct, this area duct. Now, why rho over rho is P over P? That's because what Jason said. The ideal gas, V equal rho RT. So if you make the T constant, then V over V is rho over rho. That makes P over V is M over M. And that's what you need to solve with. The last thing, really, I have 1 minute. Yeah. The last thing is that if you want to figure out what happened also inside this, you solve those 3 equations together and you'll end up with this equation. Integrating this equation is this formula. Most of the time you don't really need that formula in the solution, but sometimes you do, and it looks like a Fano curve, but it's not. You need to use this for an isothermal flow. Okay? That's it. We are done.
Yeah. You have like 30 seconds.
No.